Data Skeptic features interviews with experts on topics related to data science, all through the eye of scientific skepticism.
Okay, Linda, before I get into my interview today, I was hoping you could help me with something. Is that okay?
Sure.
So I'm going to show you a picture, but don't comment on it. Just pretend like it's a magic show and I'm the magician showing you your card, but don't tell the audience what it is yet, okay?
Mm-hmm.
All right, you see the picture?
Yes, it is familiar. It's famous, and it is familiar from our friend Matt's wedding.
Yes, it was featured at Matt and Christine's wedding, but maybe we shouldn't mention that part because this is not a photo people generally associate with weddings, although it was fitting for their occasion. I've written 3 descriptions below. In a minute, I'm going to have you read them. Maybe listeners are on Twitter and they can tweet at me if they find one of these descriptions gives away what the photo is, or if they think one is a better description than another. So, Linda, can you please read my 3 descriptions?
Yes. Option 1, 5 flags, an elaborate belt buckle, a statue of a pigeon, some white wainscoting, 2 men. Option 2, a president shaking hands with a singer, also a velvet-lined sports coat. 3, Richard Nixon shaking hands with Elvis Presley.
Okay, great. So first off, do you find all of these descriptions to be accurate?
I think so, but I'm not sure if that bird is a pigeon. I can't tell.
Okay, maybe pigeon experts can tweet about that.
I don't
too.
think that's a pigeon.
Well, okay, so then the first one's not accurate. How about the second two?
Yes.
So setting the pigeon aside, so do you think they're all good descriptions of the picture?
Well, it depends what you're trying to get at.
If you saw that photo in a gallery and each of those was the caption of it, do you think that would be appropriate captions?
No, option 3 is the only one that would probably be in a gallery.
All right, so what's wrong with the other descriptions? You said they're accurate.
Well, 5 flags, option 1, that one, isn't what people remember about the photo the most.
Yeah.
Option 2, you're getting a little closer, but you mentioned a velvet-lined sports coat. And unless it was like some fashion museum, I don't know how that's relevant.
So we're talking about maybe there's a distinction between presence and relevance. And maybe that's pretty easy for humans, but it's very difficult in computer vision. Or at least, perhaps it was until recent research in this area that we're about to have an interview about is starting to change some of that. So stay tuned and everyone else can learn about that. Thanks, Linda.
You're welcome.
Ishan Misra is a PhD student at the Robotics Institute at Carnegie Mellon University. His research interests include computer vision and machine learning. His recent paper, Seeing Through the Human Reporting Bias, Visual Classifiers from Noisy Human-Centric Labels, presents a novel way of solving a challenging computer vision task. And it's that paper I invited him on the show to discuss today. Ishan, welcome to Data Skeptic.
Hey, thanks for inviting me.
So I think the abstract in your paper very eloquently summarizes the work by presenting this dichotomy of what's in an image versus what's worth saying in the image. Can you elaborate on how these two questions are different?
So let's start by considering an image. And it's hard to show you this over podcasts, but I'll try. So if I describe a scene as 2 kids sitting in a classroom, you can agree that it's a reasonable description of a scene. Let's just take a step back and try to see what you can imagine to be in the scene. You can reasonably assume that the scene contains chairs, desks, walls, bags, crayons, whatnot. But I never described them to you in my initial description. Even though these things are in the image, they aren't worth talking about. And humans subjectively decide what to talk about and what not to talk about. These are the kind of questions we're looking at in the paper. Given an image, humans will subjectively decide to suppress certain information that is visually present in the image and only talk about certain aspects of the image.
Yeah, it's a very interesting phenomenon. I was not as aware of it until I'd read your paper, but it's very clear, and your classroom example is a good one, that there's a lot of things my imagination can come up with that are just presumed by the concise description given of 2 students in a classroom. There's a couple other really good visuals in the paper. I would encourage anyone interested in this to take a look at least at the first page there where you've got some of the quadrant of examples. Could you maybe describe some of those and highlight why those were especially good use cases for your paper?
Sure. It's like you mentioned, the first quadrant from the paper where you have concepts of bicycle and yellow. And we see images that have both these concepts present, but in their description, humans subjectively omit them. And other such examples are seen in figure 5 from right to left, where concepts present in the image are omitted. So now this poses a very inconsistent learning problem as the labels are noisy. So in this paper, we want to see if we can get around this label noise and train better models. And why should we be able to do this? Well, humans are fairly consistent when omitting parts of the scene, even though we see them. And we want to model this human thinking process into our classifier so that we can learn to distinguish what's in an image and what's worth talking about.
In those examples, we see image recognition algorithms, I guess, making mistakes, but not mistakes that are objectively false. You know, a picture that has a bunch of bananas in it and you say it's yellow, that's not wrong. So it seems to me that there's like a taxonomy of errors that are coming out here. Perhaps we could call certain errors blunders, like if a picture of bananas said it was cabbages, that's just wrong, versus having an emphasis mistake, like saying it's yellow when that's not the important feature. What are your thoughts on the right choice of vocabulary to describe these situations?
So this is actually a good question. We had a lot of debate amongst co-authors on what vocabulary to use, and even till the last day, we were actually fighting over what to use and what not to use for this one. In my personal opinion, I think errors can only be defined if you have a ground truth or gold standard or correct labels. Mm-hmm. And because the definition of these correct labels depends on your task, everything should be called an error. I don't think you should come up with different words for it. Because as long as we can describe how we came up with the gold standard, we can define an error metric with respect to that. The issue I had with using different words like blunder or error is that it makes one thing seem more acceptable than the other in all circumstances. Like a banana may be classified as a cabbage and it might be okay because you're sort of considering only food items, and that's fine.
So the paper centers around human reporting bias. Can you define reporting bias in the context of the paper?
So for us, reporting bias is when humans report or talk about only a few of the visual concepts present in an image and suppress a lot of the visual concepts present in that particular image. So when they're reporting these concepts in an image, they have a certain bias and they apply that bias when reporting such concepts.
Do you find that bias, you call it human reporting bias, and maybe this is out of scope for the paper, but do you think it's sort of standard amongst all humans that invariably us human beings would tend to label things, the same things as important, or are there cultural or age biases that will come up? How universal is the bias you see?
I do think there should be cultural and age biases that come up, and of course generational biases as well. Certain generations may prefer to describe certain visual aspects of the scene. But what we did a very small experiment for this, which is not in the paper, but this was an initial study. We took a dataset, the Microsoft Cocoa dataset, which has a bunch of captions. So for each image, we have about 5 captions, and we tried to measure the inter-annotator agreement between these captions. And we found that it was fairly high. The original authors did not actually collect statistics on age and where a geographical location and whatnot. But I do think there should be a fair amount of consistency with this reporting bias.
So I've been observing computer vision for a while. I think if we wound back 20 years, we would find it was almost not present at all. I mean, there was research going on, but it was very preliminary. And we've seen a lot of advancements to the point where image recognition is doing some phenomenal things. And we're seeing a lot of really strong proof of concepts and working technologies with computer vision. But also we're seeing a lot of these human bias errors come up. Do you think this is a new forefront for computer vision? Are we entering a new era when it's less about recognition and more about, I don't know, should we call it discernibility or just the proper annotation? Is that the new frontier, or is this just a piece of the future?
I do think this is the new frontier. I think this was actually a very neglected aspect of recognition, and people did not actually realize that our visual data really does suffer from a lot of these human reporting bias. And so we really need to consider this when we're actually, say, describing an image to a visually impaired person. We don't want to tell the human about all the million things present in an image, but only about the things a human cares about. And so this is a completely different task where the computer vision algorithms really need to change their output space to cater towards the human's needs rather than just, blindly saying cat, dog, table, blah, blah.
Yeah, that's a especially interesting use case I hadn't considered. So I think some researchers who will try and tackle this problem might claim that we should build a monolithic classifier that attempts to mimic the reporting bias. Based on your work, I would presume from an architectural perspective, you disagree. Can you tell me why?
I don't strongly agree or disagree with this one. I think for me, it's basically that you should optimize for your end task. And in this paper, we show one thing. It's that given only one type of labels, the human-centric labels or the human reporting bias labels, you can actually optimize for 2 tasks. One, the visually correct or machine-like predictions, and the second one, the human-like predictions. And so what we are showing in this paper is that modeling both of these types of predictions helps you do a better job on both of these tasks. So I don't think you should try to build classifiers that only mimic reporting bias. You should try to optimize for your end goal. If your end goal is that you want to mimic reporting bias, then sure, go for it.
Makes sense. Yeah, I think it'd be a good time to get into the architecture of your system. Can you describe how your particular setup from the inputs of all these images into your final labels is constructed and built? In my reading of it, it differs slightly from your plain vanilla off-the-shelf machine learning approach. You have these kind of two separate paths I'd love to hear some details about and why you settled on this approach.
So let's just first clarify the setup. You have an input image, and you only have these human-centric or noisy labels available. And you don't have the visually clean labels available at all. Mm-hmm. In our paper, what we say is that the human-like output or prediction can be factored into two parts. A visual presence, whether the visual concept is present in the image, and relevance. Is it relevant enough to be mentioned? What we do is we actually have a convnet which extracts a feature representation from the image. And then these features are fed into two parallel streams of classifiers. And both these streams of classifiers don't receive direct supervision. They basically model latent states in the system. The first stream of classifier predicts the visual presence output. Is the concept present in the image? And the second stream of classifier predicts relevance. Is the concept relevant enough to be mentioned by a human? Finally, we take the outputs of both these classifiers and combine them as given by a factorization equation. And we produce a human-like output. And now this is the output that we consider for computing the loss for our system. So because we had only the human-like labels to begin with, it makes sense to compute loss with respect to the human-like output. And then we end up training the system end-to-end because all the operations that I described to you are actually differentiable, so they can be modeled in a deep neural network.
So the path towards recognizing presence makes a lot of sense to me, and you have the noisy labels, so those seem helpful. But you don't have access to ground truth on relevance. Can you tell me more about how you end up optimizing for or minimizing loss for relevance?
The idea for this, when we initially looked at images which had these labels, was that when we trained a vanilla classification network, the loss would not go down. So for a bunch of images, say, let's just pick one example. For, say, banana, the network would still end up predicting yellow. Mm-hmm. And so what we assumed was if we gave the model extra capacity, it would actually be able to come up with a nice latent assignment where it could assign a high visual presence to yellow, but a low relevance to yellow, so that it can actually produce the low output for yellow. And that would end up driving down the training loss.
The concern about labeling it yellow, is that because yellow is in many other images that bear the similarity of color?
Yes.
Got it. Okay.
So even for like an image which has a yellow Vespa, which is occupying a minority part of the image in terms of pixels, you end up, the network is expected to predict yellow. But for this image, which is yellow all over, because say it's just a picture of a single banana zoomed in, you're expecting the network not to predict yellow. So it's a very inconsistent learning problem that you actually have your network addressing.
Yeah, that's very interesting. So we've touched on my next question a bit, but I want to go into it anyways. Can you talk about some of the specific advantages of solving for the visual presence and the relevance separately over trying to learn the convolution of the two directly?
I think not separating the two factors leads to two problems. The first is your labels are inconsistent. So like the yellow example. So in one image, you have a little yellow portion of the image and you want the model to predict yellow. And the other one, you have lots of yellow bananas and you don't want the model to predict yellow. So it just makes the learning process very, very difficult. And your model can't even mimic humans effectively because of this inconsistent learning. Mm-hmm. And the second more important problem is that you will never be able to learn a model that gives you visually correct predictions. At best, your model can only mimic humans. You can never get the visually correct predictions if you never separate the two factors out.
Ah, yes, makes sense. When I first started reading your paper, I assumed that eventually I was going to find the EM algorithm buried in it. It seemed like it was set up in that direction. Yet that doesn't seem to be the case. Can you talk a little bit about how you arrived at the approach you've taken?
I'm not sure if I would call it EM, but we do have a little bit of alternate optimization where we hold one set of variables constant, optimize the other, and alternate between these sets. But we only do this once. We initially train the model that predicts only a human-like label. This can be viewed as basically holding the relevance conditional constant and initialized to identity. So after an epoch of training this model, we then start training the relevance and visual presence parts simultaneously. We did think of alternating between training presence and relevance in an alternate optimization setting, but initial results suggested that the simple direct optimization approach was as effective. There is actually a reference in the paper which we found when we were writing it, which suggests that it also found similar results.
And can you talk about the improvements you saw by adopting this two separate and alternating optimizations? In terms of, if earlier you'd mentioned you tried to learn the bias labels directly, I assume you got an accuracy gain. Can you talk a little bit about the magnitude of that gain?
On certain datasets like the non-curated ones, images directly downloaded from Flickr with tags, we're actually able to double the performance of a baseline classification system. So we have gains of about more than 5% in average precision over 1,000 tags. And for the curated datasets, we're actually able to show gains of about 3% average precision across all categories, across 1,000 classes.
Wow, I think that's a noteworthy improvement. I also wanted to ask a little bit about data sets. Something interesting I hadn't thought of until you pointed it out here, that when you do image research, ideally you can work off of a large corpora of images that are really well annotated. Maybe even some graduate students have carefully gone through and labeled them. But
yes.
Of course, there's then a finite set. Those tend to be in the tens, or if you're lucky, hundreds of thousands of images. Yet the internet is positively exploding with images everywhere that have these noisy labels. Does some of your approach potentially unlock these more raw data sets for use in research?
Yes, that's definitely the case. So one thing we had in mind when we were going with this approach was that actually we should be able to harvest these social networking images which have human weak labels, which are freely available. So that's exactly why we actually show results on the Flickr images. And a lot of my work actually is in this direction, where I try to use limited supervision to improve algorithms. So as a graduate student, I did actually end up labeling about 100,000 images myself for one of my papers. And after that, I decided that I really don't want to repeat this process ever again.
Makes perfect sense, yeah. So in looking at some of the finer details, I noticed the output of the model you guys constructed is a 12 by 12 grid, and we can see some examples of that in the paper. Can you help me understand a little bit about how I interpret that, and perhaps how someone might leverage that grid operationally?
So the 12 cross 12 grid output is actually from an existing paper by Howe and colleagues. The interpretation of that is that when you look at the 12 cross 12 grid output, you can visualize which parts of the image were useful for predicting a particular output. It will actually produce a heat map which shows that, say, this part of the image was responsible for me to say yellow. So it's actually very interpretable. And a very simple application for this is where you want to localize a visual concept. So you want to ask the question, where is the car in the image, as opposed to, is there a car in the image? So it sort of tells you where the car in the image is.
That's really interesting. So I don't often find references to psychology papers in the machine learning literature I read, or computer vision literature for that matter. So I was pleasantly surprised to see you guys have delved into that area of research. Can you discuss some of the results from the field of psychology that relate to this line of inquiry?
Yes. So this actually comes in part because of a course I took in grad school, and one of my co-authors who has a background in neuroscience and psycholinguistics. The part of our work that is related to this field, it has to do with prototypical properties of objects. In our head, a lot of objects are actually represented in terms of their prototypical properties. So bananas are yellow, and so it's a fairly obvious properties. And when we are mentioning and describing these objects to other fellow human beings, we actually do not describe these prototypical properties. So like yellow for bananas, orange for pumpkins. Whenever you're writing a description, these things are never going to be mentioned. These things are just assumed to be known by everyone. You only tend to use these attributes or properties to describe objects when they're required to, say, distinguish something from something else. So you want to distinguish a yellow cup from a white cup. This is the sort of link we have to the field of psychology in this case.
When we look at a lot of machine learning classifiers, we tend to, or machine learning in general, will label certain things as supervised learning when we have some labeled examples, and unsupervised learning when we don't. And maybe that's an overgeneralization, but it's the basic idea. Part of my take in reading through this paper is that maybe there's room for something in the middle, because we could say that the human labels are ground truth labels, and therefore it's supervised learning, but there are also many things that aren't being said by the human labeler, such as, the crayons in the classroom and this sort of thing. So do you see any the same room for ambiguity I see here, that it's technically supervised but slightly unsupervised? Or I guess what's your take in general on how we describe these sorts of problems?
I think the term for this would be weakly supervised. And if you want to basically incorporate the fact that certain labels are missing or certain labels are mislabeled, you can probably just call it noisy weakly supervised.
And in this idea of maybe now we can use larger data sets on the internet, do you think we'll see a trend towards more types of research in this area?
Oh, yes, definitely. And in fact, that has been the trend in the past, say, 5 years or 3 years or so, where people have actually started moving on to bigger web-scale datasets because they have realized that just staying in the confines of pristinely labeled datasets is not going to get us further.
So I want to revisit an earlier question I'd asked you when I was saying I made the assumption that maybe the vocabulary we could use could describe these two types of misclassifications differently, and you had disagreed. What if I were to come back now, having kind of talked about your architecture, and make some definition in terms of whether or not the relevance score or the presence score contributed more to the ultimate labeling? Do you think that would be valuable for someone to say that it was the proposed label was knocked out due to relevance, and that's type A error, and the knocked out due to presence is a type B error, or is this just really a distraction from the overall line of inquiry?
No, actually, I think that's a very, very good point. We do have a figure in the paper where we do try to show how the classifier says that for certain concepts that it knows are visually present, how the relevance score can actually vary. So this is figure 5 from my paper. And I do think this is actually very important because it helps you understand what the classifier has learned. So you can actually interpret its output very easily.
Yeah, very cool. I'll definitely have that in the show notes for everyone to go check out. I think this is a good paper for anyone, whether they're a computer vision person or not. Just a little bit of ML makes it pretty accessible, and I really enjoyed it. So just to wind up, I wanted to ask you a little bit about what's on the horizon for you. What are some current projects or next lines of research? What can people look out for that you're working on next?
So I had another paper in the same conference as this one, which was on multitask learning. And the idea was that if you have a free source of supervision, say from a Kinect, which gives you depth automatically, can you actually use that to improve certain other types of supervision? So I've been working on basically using free sources of supervision to augment other more expensive forms of supervision and improve their performance. And recently I've started moving into unsupervised learning as well, just so that I can, again, harvest more and more data.
Yeah, Ishan, any place people can follow you online? Do you blog or go on Twitter or anything like that?
I don't blog, I just have my website, but I update it fairly frequently, where I do end up adding more of my papers.
Cool, and I'll have that in the show notes for everyone to check out if they're so inclined. Mm-hmm. Well, again, Ishan, thank you so much for coming on the show.
Yeah, thank you so much for having me.
Take care.
For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.